Hello everyone, welcome to the lecture series of Engineering Mathematics 1. Today this is our 6th lecture on partial differentiation. Okay, so in this lecture we are going to see some more examples on Euler's theorem. Okay, so this is our next example where we have to find x dou u by dou x plus y dou u by dou y for this is our function u is equal to x raised to 4 y square sine inverse y upon x and u is equal to x plus y plus z upon root x plus root y plus root z. Okay, so just a minute. So here first of all we solve for u equal to first function x raised to 4 y square sine inverse y upon x. Okay, let's solve for these first. So first of all we have to check the degree and whether it is homogeneous or not. Okay, so if we check here, let x is equal to xt, y is equal to yt, right? Then what is our u? If we put here x equal to xt, yes, it is x raised to 4, t raised to 4, then y square, t square, then sine inverse yt upon xt. Okay, so here this t raised to 4 in t square, I can write it is t raised to 6, x raised to 4 y square sine inverse, here t get cancelled, y upon x. Okay, so you can see here after putting x equal to xt, y equal to yt, I can write my function in the form u equal to can write here t raised to n u of xy, right? I'm getting my original function back here after putting here x equal to xt and y equal to yt. So this is in the same form. This is u xy and this is t raised to n. So here what is value for n? 6. So I can say here u is homogeneous. Yes, it is homogeneous function of degree n equal to 6. Okay, now here as I know u is homogeneous, then by Euler's theorem, what is the Euler's theorem? If u is homogeneous of degree n, yes, so here I can write by Euler's theorem x into dou u by dou x plus y into dou u by dou y equal to n into u. So you have to remember when u is homogeneous, you have to write the value for first order relation n into u. Okay, and when f of u is homogeneous, you have to write this first order relation value n into f of u upon f dash of u. Okay, you have to take a difference between two, when u homogeneous and when f of u homogeneous. F of u means z. Okay, so what is the value for n here? It is 6. And what is a u? That is a given function. So I can write here x raised to 4 y square sine inverse y upon x. So that is a value for this x dou u by dou x plus y dou u by dou y. Okay, Similarly, now I'm going to solve for this second function. Now I hope you all understood how to solve the example. You can yourself also solve. Okay, let's solve here. For the second one, always write down a given x plus y plus z upon root x plus root y plus root z. Now the same procedure we have to do here. We have to put x equal to xt and y equal to yt and z equal to zt to check whether the given function is homogeneous or not. Okay. So let's put here x equal to xt, y equal to yt, z equal to zt. Okay. So u is equal to then xt plus yt plus zt upon, yes, it is root xt plus root yt plus root zt, right? Now see what I can find here common. In numerator, t is common. What is remaining? X plus y plus z. And in denominator, what is common? Yes, we can separate the root here, root x into root t. Here also, root y into root t. And here, root z into root t. So, which term I can find here common? Definitely, it is root t upon remaining is root x plus root y plus root z. Okay. Now see here, this is t raised to 1 and this is t raised to 1 by 2. So, when I do the calculation as base is same t. So, 1 minus 1 by 2, it will be 1 by 2. So, I'll get here t raised to 1 by 2 only. And what is the function? X plus y plus z upon root x plus root y plus root z. Right? That is our u after putting x equal to xt and y equal to yt. So can we say this is again a homogeneous function? Because it satisfies the definition. It is in the same form. Right? We got here our original function back and degree is what? 1 by 2. So here u is homogeneous function of degree n equals to 1 by 2. Okay. So I can write by Euler's theorem then. By Euler's theorem. What I can write? Yes. X into dou u by dou x plus y into dou u by dou y is equal to n into u. As I told you, you have to remember the difference between two. Because we are having value for this first order relation two different. One is n into u and another is n into f of u upon f dash of u. So when we use nu, when u is homogeneous, and when we use n into f of u upon f dash of u, when f of u is homogeneous. Okay. So here I can write x into dou u by dou x plus y into dou u by dou y is equal to, put the value for n, it is what, 1 by 2. And what is u here? Yes, it is x plus y plus z upon root x plus root y plus root z. Okay, so I hope you all understood the example. I must tell you that अगर आप लोगों ने इसके पहले का वीडियो नहीं देखा है तो वो वीडियो आपको देखना है. वहां पर मैंने इसका प्रूफ लिया है और भी एग्जांपल्स इसके पहले के वीडियो में मैंने सॉल्व कर दिए हैं. ओके, आपको ये पूरा सीरीज सिक्वेंशियली ही देखना है. यू हैव टू सी दिस कंप्लीट सीरीज सिक्वेंशियली, देन ओनली यू कैन अंडरस्टैंड दिस पार्शियल डिफरेंशिएशन यूनिट. ओके, don't watch any one of the video in middle. Okay, try to watch in sequence. Let's have a next example here. Now this is the next example. I must write here too. So we have to just a minute. Yes, here it is our second example. If u is equal to f of y upon x plus root x square plus y square, then prove that x into dou u by dou x plus y into dou u by dou y is equal to root x square plus y square. This we have to prove. Okay. Now see here. What is given to us? Already this kind of example we have solved in previous lecture. Okay. U is equal to f of y upon x plus root x square plus y square. Okay. So let's write it. U is equal to in the form v plus w. So therefore here we can consider v is f of y upon x and w is root x square plus y square. Okay. So now concentrate on this function v. What is the degree of this function? See, in numerator degree of y is 1 and in denominator degree of x is 1. Okay. So this is a very simple way to find a degree. Numerator degree minus denominator degree. So 1 minus 1 it is what? 0. Right? If I put x equal to xt and y equal to yt, t get cancelled. Means there is no term of t. Right? So I can adjust here t raised to 0. So according to that, I can say this v is a function which is homogeneous of degree n equal to 0. Okay, I hope you all understood. So here v is homogeneous function of degree n equals to 0. Okay. Therefore, by Euler's theorem, what I can write? Yes, I can write x into dou u by dou x plus y into, just a minute, as I am saying here, v is homogeneous. So I have to write there v, not u. Okay. So here this must be v because we are talking about v. V is homogeneous of degree 0. So I'll get the relation of first order for v by Euler's x into dou v by dou x plus y into dou v by dou y is equal to n into v. But what is n? It is 0. So therefore the value for this first order relation becomes 0. Okay. Say this is our equation. Suppose here I say this is 1 and this is 2. Okay. Now next, also talk about w. See, this is your w. When we say the function is homogeneous, when each term of your function have same degree. Okay. So here, this is your term x square. What is the degree? 2. This is your term y square. What is the degree? 2. Means each term is having degree 2. But when I find it from square root, outside the square root, okay, its degree becomes 1. Right? So here I can say w is homogeneous function of degree n equals to 1. So if it is not possible to find directly the degree of given a homogeneous function, okay, you can use the method, put x equal to xt, y equal to yt and then find its degree and check whether it is homogeneous or not. That also you can do. Okay. So here w is a homogeneous function of degree 1. So I can use the Euler's theorem because it is homogeneous. So by Euler's theorem, what I can write? Yes, x into dou u by, just a minute, it should be w. dou w by dou x plus y into dou w by dou y is equals to n into w, right? Because our function is w and it is homogeneous of degree n equal to 1. Now putting here value for n and w. So this will give me x into dou u by dou x plus y into dou w by dou x plus y into dou w by dou y is equal to, what is n? It is 1 into then w. What is a w? Yes, it is root x square plus y square. Okay, so let's say this is an equation 3. Okay, so here now what we have to prove, you can take this is our left hand side and this is our right hand side. So now we are going to solve our left hand side. So consider the left hand side from the proof. What is it? X into dou u by dou x plus y into dou u by dou y, right? But I have considered value for u from equation 1. You can check what is u? V plus w. So put here u equal to v plus w. What I get? That is equal to x into dou by dou x into v plus w plus y into dou by dou x v plus w. Okay, so here x into dou v by dou x plus x into dou w by dou x plus y into dou v by dou x plus y into dou w by dou x. Just a minute, should be y, right? Okay, so this we got here. Now v with v, write down. So I can write here x dou v by dou x plus y dou v by dou y plus x dou w by dou x plus y dou w by dou y. This we can write. Okay, and we have value for this. What is the value for this one? Yes, from equation 2 I can write the value for this is 0. So here it is 0 plus what is the value for this? From equation 3. Here you can see. Okay, I can write it very clearly here. It is 3. Okay, so from equation 3, what is the value for this one? This root x square plus y square. So what is remaining then? At last it is root x square plus y square, which is our required right hand side. Okay, so we can say here, hence proved. Okay, so this is how we have to solve the examples based on Euler's theorem. Okay, but you can use Euler's theorem only for those functions which are homogeneous. Okay, let's have one more example on this. So here you can see u is equal to x cube plus y cube upon y root x, and we have to find first order relation as well as second order relation. Both we have to find. Okay, so first of all we are going to write the given part. What is given here? U is equal to x cube plus y cube upon y root x. Okay, now I have to check here degree. You can see each term should have same degree. Okay, so here there are two terms. What is the degree? 3. Here also what is the degree? 3. Means in numerator common degree is 3, and in denominator what is the degree for y? 1. Now this is a complete term because there is a multiplication sign. Okay, when terms are separated, when there is a plus or minus sign between the terms. Okay, but here multiplication sign, so this is a complete term. What is the degree for y? 1. And what is the degree for x? 1 by 2. Adding together 1 plus 1 by 2. Yes, it is 3 by 2. And now what we have to do? Just we have to subtract this 3 minus 3 by 2. So what I get here, if I do 3 minus 3 by 2, yes, it is 6 minus 3 by 2 means again I'll get 3 by 2. Is it clear to all? Okay. So this is our m. So see, without putting here x equal to x10, y equal to yt, you can check whether the given function is homogeneous or not, and also you can find its degree very easily. Okay, you can also choose this method to find its degree. So here, now u is a homogeneous function. U is homogeneous function of degree n equals to 3 by 2. Now u is homogeneous, therefore by Euler's theorem, what we can write? Yes, x into dou u by dou x plus y into dou u by dou y is equal to n into u. So what we get? Definitely put here value for n, it is 3 by 2, and u is what? Your given function. So you can keep it as it is also u. So this is your value for first order relation. Also, by deduction of Euler's theorem, I can write the value for second order relation. What is it? X square dou 2u upon dou x square plus 2xy dou 2u upon dou x dou y plus y square dou 2u upon dou y square is equal to n into n minus 1 into u. Okay, so here also for the second order relation there are two values we have. One is n into n minus 1 into u, and another is g of u in bracket g dash of u minus 1. So when we use these values, when your u is homogeneous, you have to write the value for second order relation this, n into n minus 1 into u. But if f of u is homogeneous, then you are going to write the value for this second order relation g of u in bracket g dash of u minus 1. You have to remember difference between these two. Okay. Now here our u is homogeneous, therefore I have to use this value. And what is n? Yes, it is 3 by 2. Then again 3 by 2 minus 1 into u. Solve this. So 3 by 2 into 3 by 2 minus 1. What we can write? Yes, it is 1 by 2 into u. Okay. And finally we can write the answer 3 by 4 into u. So for second order relation, I have value 3 by 4 into u, and for first order relation, I have value 3 by 2 into u. Okay. So these are the required answers for your example. Now let's have one more example on these. This is our next example. What we have to do here, see, u is equal to x square tan inverse y upon x minus y square tan inverse x upon y, and then find the value of this second order relation that we have to find. Again do the same, write down your given part first. So u is equal to x square tan inverse y upon x minus y square tan inverse x upon y. Okay. Now here there are again two functions which is separated by minus sign. So I can write here, let u is equal to, yes, what we can write? Correct. So we can write here v minus w. Okay. But if we check here, v is homogeneous function of degree. What is the degree here for v? Yes. Here x square means t square if I put x equal to xt. Right. And if I put here y equal to yt and x equal to xt, t get cancelled. Means only t square remains. Means degree is what? 2. Right. And w is homogeneous function of degree. Again here, what is the degree? If I put y yt, x xt, again y yt, t get cancelled here, and here t square is remains. Again degree is 2. So when you are having two functions of same degree, we can directly write the answer by Euler's theorem. Okay. So therefore, by Euler's theorem, what I can write? So here, by Euler's theorem, I can write x square dou 2u upon dou x square plus 2xy dou 2u upon dou x dou y plus y square dou 2u upon dou y square is equal to, yes, n into u. Because now I am having here degree same. So what is the value I can write? N into, what is our u? Yes. Write down here x square. Just a minute. This is a formula for first order relation. We have to write here n into n minus 1 into u. Okay. So just erase. Okay. So we can write it is, what is n? 2 in bracket 2 minus 1 into u. 1 and the same thing we are getting here, same answer, that is 2u. Okay. And here you can write the value for u also. So it will be x square tan inverse y upon x minus y square tan inverse x upon y. Okay. So that is your final answer. So I hope you all understood the example. Let's have a next example on the same Euler's theorem. So here what I have to do, this is a function given to me and I have to prove this for this second order relation. Okay. So first of all, always write down the given part. What is the given part here? Yes, u is equal to sine inverse x plus y upon root x plus root y. Okay. Now take the degree here. In numerator, what is the degree? 1, and here also 1. Means a common degree is 1. And in denominator, what is the degree? 1 by 2, 1 by 2. Means common degree is 1 by 2. And if I do this, 1 minus 1 by 2, what I get? 1 by 2. Okay. But here I am getting 1 by 2 sine inverse. For sine inverse. Okay. What I have to do? If suppose this value is 0, I don't have to transfer this sine inverse on left hand side. Okay. But if suppose this value for n is non-zero, whatever is function, here you have to transfer this on left hand side. And that function will be homogeneous function of degree this, whatever is your answer. Okay, so I can't say here now u is homogeneous. I have to say therefore transfer this sine inverse on left hand side, that will becomes sine u. Sine u is homogeneous of degree n equals to 1 by 2. Okay, so always you have to remember, if you are having here value non-zero and your function having any trigonometric or inverse function or logarithmic, then you have to transfer this function with u. Okay, and then that will be your homogeneous function of degree, whatever degree you have. Okay, so here sine u is homogeneous means f of u is homogeneous, function of u is homogeneous, right? So therefore by Euler's theorem, what we can write? Yes, x square dou 2u upon dou x square plus 2xy dou 2u upon dou x dou y plus y square dou 2u upon dou y square is equal to, now here f of u is homogeneous, so definitely I can't write here value for the second order relation n into n minus 1 into u. I have to write that value n into, just a minute, it is second order relation, so it is g of u in bracket g dash of u minus 1. But what is g of u here? Yes, where g of u is equal to n into f of u upon f dash of u. This is a value. So if I put here n is 1 by 2, and what is f of u? It is sine u, and I have to take a derivative of f of u, f dash of u. So derivative of sine u, it is cos u. So what I get here? 1 by 2 tan u. Okay, now g of u I got 1 by 2 tan u. I have to find g dash of u. So what is the g dash of u? Yes, it is a derivative of tan u. And what is the derivative of tan u? It is sec square u. So here I got the value for g of u and g dash of u. Putting this value here in equation 1c. So what I get, see, from equation 1, x square dou 2u upon dou x square plus 2xy dou 2u upon dou x dou y plus y square dou 2u upon dou y square is equal to, put the value here. So here, what is our value for g of u? By using this formula, we have to put here value for g of u and g dash of u. So g of u is 1 by 2 tan u, right? 1 by 2 tan u in bracket g dash of u minus 1, and g dash of u is 1 by 2 sec square u minus 1. Now see, you can see your proof here on right hand side. We have terms in sine and cos. So we have to convert this tan and sec into sine cos. So using the relation, what I can write? Yes, it is sine u upon cos u. Then 1 by 2 into sec square u, what I can write? Yes, it is 1 upon cos square u minus 1. Now do the cross multiplication here. What I can write? 1 by 2 sine u upon cos u, right? And it will be 1 minus 2 cos square u upon, yes, it is 2 cos square u. But we all know the result. 2 cos square theta minus 1 is equal to cos 2 theta. And if I want to use this result here, I have to take a minus sign common. So what I can write here in bracket, if I take a minus sign common, yes, it will be now 2 cos square u minus 1 upon 2 cos square u. Okay. So here 2 cos square u minus 1. What it will be? Cos 2u. So I can write this is minus 1 by 2 sin u cos 2u upon cos u into cos square u. What is it? Yes, it is cos cube u. And these 2 into 2, it will be 4. Okay, let me write. Instead of 2, there comes 4 after multiplication. This is 4. And which is our required right hand side. Okay, hence proved. So in last lecture I already told you, if we have to find a second order relation when your f of u is homogeneous, simply we have to put the values for g of u and g dash of u. If they ask you to find the value for second order relation. Okay, but if they ask you to prove for second order relation is like this something, then you have to do necessary adjustment as we have did here. Okay, so by doing that necessary adjustment, we have to prove our right hand side. Okay, let's solve the next example. So this is our next example that we have to solve here. See, this is given function and uxx, uxy, uyy means what? They are double derivatives of function with respect to x and y. Okay. So here, first of all, always write down your given part. What is the given part here? U is equal to sine inverse x raised to 1 by 4 minus y raised to 1 by 4 upon x raised to 1 by 5 plus y raised to 1 by 5. Okay. So here we have to find a degree of this homogeneous function. It is homogeneous, we can see. In numerator, each term having same degree. In denominator, each term having same degree. Right? So here, what we can write? Yes, degree in numerator is 1 by 4. And degree in denominator is what? 1 by 5. And doing the subtraction, what I get? 1 by 4 minus 1 by 5. And if we solve this, it will give us 1 by 20. Okay. So, it is a homogeneous function of degree 1 by 20. But who is homogeneous? U or f of u? As I told you, if you are having here some function, maybe trigonometric, maybe inverse trigonometric, logarithmic, okay, and degree of the function with that is not 0, then you have to transfer this on left hand side and that function will be homogeneous, right? Because here our degree is non-zero, it is not 0. Okay, so we have to say here, therefore f of u is equal to sine u is homogeneous function of degree n equals to 1 upon 20. Okay. Now, by Euler's theorem, what we can write? Yes, we can write here for second order relation x square dou to u upon dou x square plus 2xy dou to u upon dou x dou y plus y square dou to u upon dou y square equals to g of u in bracket g dash of u minus 1. Okay. What is the g of u here? Where g of u is equals to n into f of u upon f dash of u. Right? So here, putting the values, what is n? It is 1 by 20. What is f of u? Yes, this is our f of u here. Okay. It is sine u. And what is f dash of u? Definitely it is a derivative of f of u. So derivative of sine u, it is cos u. Okay. So therefore I got here value for g of u. It is 1 by 20 tan u. And from this I can find g dash of u. So taking a derivative here, what is the derivative of tan u? Yes, it is sec squared u. Okay. So I got the value for g of u and g dash of u. Simply now I have to put here. So therefore, let's write, this is our equation 1. Okay. So I can write here from equation 1, x square dou 2u upon dou x square plus 2xy dou 2u upon dou x dou y plus y square dou 2u upon dou y square is equal to, yes, put the value for g of u. What is the value for g of u? We find 1 by 20 tan u. So I can write here 1 upon 20 tan u in bracket. What is the value for g dash of u? Yes, it is 1 upon 20 sec square u minus 1. Okay. That is, I can write x square u xx plus 2xy u xy plus y square u y is equal to 1 by 20 tan u in bracket sec square u upon 20 minus 1. Okay. So this is our final answer. We don't have to solve it further. Okay. They just ask you to find the value for the second order relation. अगर यहाँ पर होता prove that, तो हम लोगों को यहाँ पर इसके adjustment करनी पड़ती. No, we have to do the adjustment to find a required answer that we have to prove. So here we can leave the example here also. So these are examples based on Euler's theorem that we can solve with the help of Euler's theorem. So Euler's theorem, when we use, when your function is homogeneous, only then we can use Euler's theorem to find the value of first order relation, second order relation. Okay. What is the main statement of Euler's theorem? Yes. If u is a homogeneous function of xy of degree n, then x into dou u by dou x plus y into dou u by dou y is equal to n into u. Right? And for second order relation, when u is homogeneous, now all remaining three are now the deduction of this main statement. Okay. So the second order relation, then x square dou 2u upon dou x square plus 2xy dou 2u upon dou x dou y plus y square dou 2u upon dou y square. When u is homogeneous, it is n into n minus 1 into u. But when f of u is homogeneous, value for first order relation is n into f of u upon f dash of u. Right? And second order relation, g of u in bracket g dash of u minus 1. So you have to always check whether u is homogeneous or f of u is homogeneous. Then you are going to decide which result we have to use. Okay. So I hope you all understood the Euler's theorem very well. Thank you all for watching this lecture series. In next lecture, we are going to cover our next article, change of independent variable. Thank you.